So we are on page 52. We're going to continue doing a couple more just application questions. And then we're going to talk a little bit about sinusoidal regression, which will be a good little review of regression, because we haven't done that in a while. And then we're going to be done this unit. Yeah, that's right. Okay. Carmen, is everything looking good? Yeah. Awesome. Thank you. Okay, so height of a chair on a Ferris wheel follows the function h equals 5.7 sine 0.31 t plus 7.9, where h is the height in meters and t is time in seconds. How high is the bottom of the Ferris wheel off the ground? This is on page 52, in case you just are catching up to speed now. Okay, and before we actually answer any of these questions, what I'd like to do is just take apart this equation a little bit. Because over the past few days, we've looked at the equation of a sinusoidal function, and we've looked at what three parameters mean. And we have three parameters here in this sinusoidal function. We've got this guy, we've got this guy, and we've got this guy. Okay? So let's start with the 5.7. What does that tell us? How would you describe that on the graph? This number in front of the sign. The amplitude, yeah. Okay, and what about the 7.9? Midline. And the 0.31? Is it equal to the period? Affects the period. Okay, so how would we figure out the period based on the 0.31? Yeah, that's right. So the period is 2 pi over 0.31. Okay, can someone tell me what that is, please? $20.3? Thank you. Okay, 20.3. All right, so we can kind of imagine what that might look like on a graph. And in fact, what I might do is, even though we can look at it on a calculator, and we might do that in a second, I'm just going to think about this. So my midline is at 7.9, so let's just put in 7.9. Whoops. Okay. My amplitude is how high the wave would go, or how low the wave would go above or below the midline. So the amplitude is 5.7. So if it's going to go 5.7 up from 7.9, how high will it go? How high will it go up to the very top? 13.6? Yes. How'd you get 13.6? Yeah. You just add the 5.7 from the midline, right? Because you're going 5.7 above 7.9. So here's 13.6. Okay. And then I'm going 5.7 below 7.9. Where's that? 2.2. Is that 2.2? Okay. Okay. And so it's going to look something like this. Okay. And this is one period. What should this time be? 20.3. Yeah, because we just figured out what that period was. Okay, so, and by the way, this is where the 5.7 comes, right? This over here and this over here, these are both 5.7. Okay, now let's actually imagine how this plays out on the Ferris wheel. Here's my Ferris wheel. Okay. Where's the number 7.9 going to show up in the picture of my Ferris wheel? Here's the graph of the function. What's the 7.9 going to correspond to on the Ferris wheel? The center, yes. Because remember, the wheel moves around the 7.9. So here is the 7.9. I need to move it a little bit to the left. Okay, and then the max, right, is the 13.6. The min is the 2.2. What does the 5.7 correspond to? The radius of the wheel, that's right. There we go. Okay, and what about this 20.3 business, the period? Yeah, that's how long it takes to go all the way around the wheel once. And that's time in seconds, okay? So this is kind of like, here's the graph, here's a picture of actually what's going on if you're riding this Ferris wheel. Okay, so first question is, how high is the bottom of the Ferris wheel off the ground? Well, that's 2.2 meters. So I'm thinking probably if you have to get up to this thing, you're going to have to like climb some stairs. Because 2.2 meters is pretty high. Okay. Another Ferris wheel can be modeled by the function y equals 7 sine 0.31x plus 9.9. Compare the two Ferris wheels. So I talked a little bit about comparison in a question that we did yesterday. If we're doing a comparison, what are the things that we should be speaking to? Comparison. For a sine function, let me add that bit in here. Yeah. Okay, well, we might do that, yes. But in general, if we were asked to compare one sine function to another, for this particular example, yes, that would be a good thing to do. But in general, if you're going to compare one sine function to another, what things should you speak to when you're doing the comparison? Yeah. Yeah, amplitudes. What else? Yep. Midlines. What else? Periods. Yes. So compare the parameters. Okay? Compare the two Ferris wheels. Well, we need to compare the parameters in context to the wheels. Right? So we have to think about parameters in this particular context mean something about the wheels. And that's what we need to compare. Okay? Well, what do you notice, firstly, is the same in terms of the parameters? The periods. Yeah, the 0.31 is the same. The b values are the same. So one thing we can say is that they both take 20.3 seconds to go around once. Okay? All right, let's maybe start with the midline. This midline is 9.9. The other one is 7.9. What does that mean about this Ferris wheel compared to that one? Where does the 7.9 show up in this Ferris wheel? It's the midline of the graph, but where does it show up in terms of the Ferris wheel? It's the height of the center. Yes. So this second Ferris wheel, is it going to be the same? No, it's 2 meters higher. So the second Ferris wheel's wheel, the second Ferris, how do I spell it? 2 R's. Wheels, wheel, or I should have, you know what, I'm going to say this differently. I'm trying to think of how I'm going to construct this English sentence. I'm doing some editing, some English editing. This is how I'll say it. The second wheel's center, that's better, is 2 meters higher. Why is what 1.3? We're 1.3. What?
Because the midline is, just kidding.
What?
Sorry, I got confused with the numbers.
Oh, yeah, okay, okay, okay. The second wheel's center is 2 meters higher because instead of it being 7.9 meters above the ground, it's 9.9 meters above the ground. Okay. What about the fact that this is 7? What does that mean? The amplitude 7, how does that show up in the wheel? Not the range, on the wheel, the radius, yeah. Second wheel's radius is how much bigger? 1.3 meters bigger? Is that where the 1.3 came in? Okay, there we go. 1.3 meters bigger. Okay, now will that affect that will affect the range, right? Where's the lowest point going to be? If the middle is at 9.9 and then you go 7 meters down, where's your lowest point going to be? 2.9. Yeah. Right? Because you're going 7 meters below 9.9 is now 2.9. Where's your highest point going to be? If your middle is 9.9 and you go 7 meters up, 16.9. Yeah. Okay. So I'll do this here. So your lowest height is 2.9, and you might want to put in brackets 9.9 minus 7. And your highest height, I feel like that's highest height. Like that should be a song or something. I think it is a song. Is 16.9, which is 9.9 plus 7. Living on the wild side, you're going a lot higher on that one. Now in part C, what's the domain and range? Now we're talking about the original, of the original. If the ride lasts 3 full rotations. We're going back to the original. Let's talk about the range first. That's like the range in heights. What possible types of heights could you have? What's your lowest height? What's your highest height? 2.2, 2? 15 or 13.6, yeah. So for this is, by the way, for the original. Okay, so the range is going to go from 2.2 to 13.6. Domain. So domain is time. This ride is going to last 3 rotations. How long is it going to take to go around 3 times? Yep. 60.6, almost. 60.9, yes, because each rotation is 20.3 seconds. So 3 rotations will be 3 periods. Okay. Three times 20.3 seconds. Okay, so the domain, the starting time is 0. Oh, you know what? Instead of y, I'm going to use h for height. Is less than or equal to time, which is less than or equal to 60.9. Okay, so that's that one. Questions with that so far? No? Okay. I am going to skip this one for now, and I'm going to get you guys to work on that later, and I'll skip this one as well. Actually, no, let's talk about this one. Actually, no. Let's talk about this one. Okay, go to page 54 and go to the second example at the bottom. Over here, it says a Ferris wheel has a radius of 8 meters and its center is 2 meters above the ground. A rider gets on a chair of the Ferris wheel at its lowest point and completes 1 full revolution in 48 seconds. If the function y equals a sine bx minus 1.57 plus d, where y represents the height of the rider above the ground in meters and x represents the time after the ride has started, I should say can model this situation, but I didn't, determine how long the rider is 15 meters above the ground in 1 cycle. All right. What do you think would be a good place to start? Excellent. Did everyone hear that? No? What do you guys think would be a good place to start? Draw it. Good answer. Yes. So we're going to draw a picture. Here's our ground. Here's our Ferris wheel. You do not have to be very good at drawing to do this. I'm not very good at drawing, as you all know. And all you need really is like a triangle to hold the Ferris wheel up and a circle for the Ferris wheel. Okay. And what are some things that we should put into this picture? What's some information? Yeah. Yeah. What's some information that we should put? Oh, and actually when I'm doing this, you know what I like to do? I like to just put in a little y-axis, just so that I can keep track of maybe some heights that might be important. Okay, so what do you think are some things that might be important to put onto this scale, on this vertical scale? Yep. Yeah, radius is 8. Okay, so that's 8. This is also 8, by the way. Okay, that's good. What else? 10 meters above the ground. So which point is at 10 meters? The center, yes. This over here is at 10. Okay. Well, then could we put in some other heights? What would the lowest height be? It would have to be 2, exactly. Because if this is 10 and then there's a chunk of 8 for the radius, then this part over here has to be 2, right? Because 2 plus 8 is 10. And then what about the maximum height? 18, exactly. It's going to be 10 plus 8, which is 18. Okay, so this is good. All right, we got a little picture of what's going on. What do you think we should do next? Okay, something with the formula. What about substituting the formula? We've got this formula or this equation, an equation of a function. Y equals a sine bx minus 1.57 plus d. Okay, so this is an example, by the way, of where you have that c value, that parameter that I told you about c, that moves the graph from side to side, which will always be given to you if it's involved in one of the functions. So it's given to you here. You just need to plunk it in there, and otherwise you don't need to worry about it. Okay, so what do you think we might do with this? Yeah. Yeah. We can start to fill in some parameters, right? Do we know what the amplitude is? Yeah, what's the amplitude? 8. Okay. Do we know what the midline is? 10, because that's the middle of the wheel, or the height of the middle of the wheel above the ground. Okay, what about the period? So the period is 48. Is that going to be the B value, though? No. How would we get the B value? Period equals 2 pi over 48. So actually, if you don't remember what it is, then we have to know how to solve for it. So period is 2 pi over B, okay? We know in this case that the period is 48, so we can put a 48 on the left side. Now we have to solve for B. How would we do that? Yeah. Yeah. Multiply both sides by B to get it out of the denominator. Here's a little review of rational equations. Of course, B cannot equal 0. Okay, so we've got 48B equals 2 pi. And now what? Divide by 48. Okay? So we get that B equals 2 pi over 48. Now that ended up being B equals 2 pi over the period. So what happened is that the period and the B value in the equation or in the formula just swap places. If you can remember that, you could take that shortcut. If you don't remember that, you need to know how to solve for B. Okay? Now, you could write that in as a decimal if you want, but if we're going to enter this into our calculator, I would suggest that you don't, just because if you're entering a decimal, it's going to be a rounded value, right? You're going to have to round it at some point, and then you're like cutting down the accuracy, right? If you did want to enter it in, I don't know, what's 2 pi over 48? 0.13. Okay, so you could enter that in, but you could also just enter 2 pi over 48, or divide 2 divided by 48 is 24 pi over 24. Either one is fine, it doesn't matter. You don't have to reduce it, but I would leave it this way. You could write it as 0, it's 0.13. Is that right? Okay, you could do any of those, okay? All right, so that's our B value. So that's pi over 24 x minus 1.57 plus 10. Okay, so we've got our function. That's good. The question is asking, determine how long the rider is 15 meters above the ground in one cycle. Now, we're told that the rider, where does the rider start? It says a rider gets on the chair of the Ferris wheel at its lowest point and completes one cycle in 48 seconds. So if we were to kind of draw a picture of this, and we can do that once we have the wheel, right? We have the 2, we have the 10, we've got the 18, and trust me, we're going to graph this on our graphing calculator in a second. Right? Where do they get on the ride? Yeah, at the bottom, right? And they're going to go up and back, down. That's one period. Up and down. Okay? What would this time be over here? This is 0. What's this time going to be? 48, because that's one period, exactly. That's how long it takes them to get back to where they started. Okay. Now, what are we actually being asked for in this question? Yeah. 15 meters above, yeah. How long are they above 15 meters? Now, we've looked at these types of questions before when we looked at other types of relations and functions. You gotta go? Oh, okay, yeah?
Would you put 15 in y2?
Yeah, so 15 meters, does that represent the variable x or y? Y. So if you have a y value and you need to figure out x values, we need to plot a horizontal line at 15 and find intersection points. And once we find these intersection points, we can figure out, okay, well, what's that time? What's that time? And then we can find the amount of time that it's above 15 meters. So this is kind of a roadmap of what we're going to do. Okay? Now let's get out a graphing calculator and actually do it. So firstly, we've got to enter in our function. Oh, you know what? I was just doing trig with another class. I'm in the wrong mode. Oh, no, I'm in the right mode. Okay, sweet. So y1, 8 sine pi divided by 24, or 2 pi divided by 48, either one, x minus 1.57. By the way, do you guys know what the 1.57 actually is? It's a rounded value. Do you know what it actually is? It's pi over 2. 3.14 divided by 2 is 1.57. Bracket plus 10. And my second line is going to be 15. Okay? And now I need to think about my window settings. Okay? So firstly, x represents what? What does x represent? Time. What do I want to be able to see here for my time? What do you think would be valuable to see? 1 period, yeah. So I'm going to make my x min 0 and my x max 48. Okay? Now this actually looks good for my y values because my lowest height is 2 and my highest height is 18. So this looks great. 0 to 20, then I can see everything, right? So for your y, you want to think, what does y represent? Its height. What heights do I need to be able to see? And then you can set your window settings accordingly. Okay? And then I'm going to hit graph. There we go. And there we go. Okay? And then I can go and find my intersection points. There's one of them over here. That's 17.15. So what I'll do is I'll just put that in this picture over here. So this right here is 17.15, 15. That's this point. And then this point is, let's see, we'll do that again. And actually, if you have a Casio, you don't even have to plot the horizontal line. You can just put in a y value, it gives you the x value, so that's kind of nice. Those of you with Casios are well ahead of me. Enter, enter, enter. 30.84. Okay. So this is 30.84, 15. Okay. So how would you figure out the amount of time that the rider is above 15 meters? Yeah. Yeah, exactly. Subtract. It's the difference between the two times. So it's 30.84 minus 17.15. And that's 13. What does it tell us to round to? Did I say anything about that? Oh, well, let's round to the nearest tenth. That's, I think, 13.6 to the nearest tenth. Is that right? There we go. I just picked the nearest tenth so I could do it nicely in my head. Okay, does that make sense? Yeah, so the key here is, what did we have to do? Okay, we had to be able to visualize what was going on so that we could see what the midline, the amplitude was, and also the period. Then we could determine an equation to model the situation, and then we could use that equation to solve the problem of how long are we above 15 meters. All right, questions with that? Okay, so we did this one yesterday. What I would like you guys to do now is to try questions 2 and 3 on page 55. Okay, and for those of you, hold on, I'm just going to pause my recording. About what the picture would look like. Yeah, question? No? Okay. So again, I'm going to reference Little House on the Prairie, because this is what I think about when I think of the water wheel and the mill. And did anyone here watch House on the Prairie? Oh, you know what I'm talking about. There you go. Okay. I don't even know where you can watch it these days. Oh, that's a good idea. Rent it. Why didn't I think of that? Okay, so a water wheel is used to power lumber mills in historic recreations. A typical wheel makes one complete revolution every 90 seconds. A paddle starts its cycle at its lowest point 1 meter below the level of the water. So what I'm going to do is I'm going to draw some water. And the wheel starts 1 meter below the water. So here's where the wheel starts. And it reaches a height of 4 meters above the water. So it's actually going underneath the water. Okay? Here's the middle of the wheel. And so what I'm also going to do is I'm going to draw this in. What do you think the water level should be? 0. Yeah, that's right. So what is this minimum going to be? -1. Yeah. And the maximum? 4. Because it goes 4 meters above. Okay. And then it takes, how long does it take to go around? It takes 90 seconds to go around. So once you have the min and the max, and you have the 90 seconds around, you should be able to solve the rest yourself, because you can get this equation, right? And from min and max, you can get the amplitude and the midline. And then from the 90 seconds, you can get the period. Okay? And then what you're being asked for in this question is, for how long is it below the level of the water, right? How long is it underwater? And so it's going to be similar to the one with the Ferris wheel, where we were like, how long is it above 15 meters? It's the same type of question. Okay? All right, are you guys ready for the very last thing we have to do in all of relations and functions? Yes? Okay. Well, the good news is we've done it before. It's regression. Regression. Okay, so just remind me, what's sort of the general idea behind regression? What are we doing with regression? When we did linear regression or quadratic regression or cubic or exponential logarithmic, those are the ones we've done so far. What were we doing? Yeah. So we were plotting, we had a bunch of points, right? So if we, like, for example, it was like a scatter plot. Let's say the scatter plot looked like this. And we fed the calculator all of those data points as like x, y coordinates. And then what could we do when we performed a regression? Yeah, we could get a line of best fit or a curve of best fit. In this case, we'd probably want to get a line of best fit because it looks like it's going to be linear, right? And that's probably what you've done in science class before when you're doing some, like an experiment. And we basically learned how to use technology to do that. Okay, well, we can do that with sine, with data that could be modeled using a sinusoidal function as well. And so we're going to finish off with that today. Now, a sinusoidal regression takes this form, y equals a sine bx plus c plus d, which is nice. Okay, that's what we've been used to. And so it has the same 4 parameters that we've seen. Okay, again, you will never be asked anything about c, but you'll just need to know, like, you're going to get a c value, you plug it into the equation. Okay? So let's look at an example. Celeste lives in Red Deer, Alberta. The predicted hours of sunlight for 1 year are shown in the table below. Okay, so we've got January 1st, February 1st, March 1st, etc. So all the firsts of the months. Okay, and then we also have the day number. So this is the day number in the year. So January 1st is, we've got some sign language going on here. January 1st is day 1. Why would February 1st be day 32? Yeah? Yeah, because like January 31st is day 31, and the day after, which is February 1st, is day 32, right? So this is why, and then I guess there's 28 days in February, so 31 plus 28 is 59. So once you get to February 28th, you're at day 59, which is why March 1st is day 60. Does that make sense? And so on and so forth until you get to December. And we're going to assume, I suppose, that this is not a leap year, and February does not have 29 days. Okay? And then over here, we have the length of the day in hours. This is the number of hours of sunlight that we have on that particular day. So the first thing that we're being asked to do is determine the sinusoidal regression function that models the data, rounding all parameters to the nearest hundredth. So I can model this. Oh, you know what? I only have the TI emulator on this laptop. So that's what I'm going to use for now. But what I can do is I could prepare a little video using the other emulator if you want, and I'll post that to D2L. Okay, so I'll do the same, because I know some of you guys have Casios. So follow along with me. After school today, I'll do a little demo on the Casio using my other laptop, and I will post that to YouTube. Yeah? Yeah. Okay, so do you guys remember where we have to go to enter in all of our data? What button do we have to press? Stat, that's right. And we have to go edit to edit our lists, okay? Mine are empty, but if something was in there, you could go up to L1 and just hit clear and enter, and that will clear everything all out of the lists, okay? And what we're gonna do in L1 is we're gonna enter in our X values. Now, should that be January 1st, February 1st, March 1st, et cetera, or should I put the day number? The day number, that's right. Okay, this is not gonna be what I want it to do. It's gonna start switching back and forth. Where did my notes go? Oh no, my calculator rather, there it is. Okay. You know what? Could you pass me a booklet? Because now my notes have disappeared on me. Thank you. So I need to just look up, what page are we on? 56? We're on page, oh no, this is the wrong one. Okay, I'm gonna just close my calculator for now. You guys will get a head start. And I'll go back to here. Okay, there we go. And now I'm going to open my calculator again. Hopefully it won't do this to me again. This is where I need to play the Jeopardy theme song. Okay, here we are. So I'm going to enter in 32, 60, 91, 121, 152. Whoops. Oh, for crying out loud. $152. I gotta stop talking to myself when I'm making videos. I keep forgetting that those are gonna go, that my thoughts out loud are gonna go into my videos as well. Okay, 182, 213, 244, 274, 305, and 335. Okay, and then in L2, we're gonna put our Y values, or our, not our Y values, but our lengths of the day. Okay, I think I'll be able to do it this way. Okay, 7.8. Whoops. 9.1. 10.9, 13. 14.9, 16.5. 16.7, 15.5. 4 more. 13.6, 11.6, 9.6, 18.1. Is it 8.1? 8.1. Okay, there we go. I think I got everything in there. Okay, next, what do I do next? Let's say I wanted to see what this looks like as a scatter plot. What would you have to do to look at the scatter plot? Yeah. Yeah, go to y equals. First, like, clear everything out the way, and then when you're doing stuff with the regression, your plot 1 has to be highlighted. So you got to make sure that that's highlighted. And then if I hit graph, would I see anything? Probably not, because my window setting hasn't been set properly. So how could I set my window setting? There's a built-in setting. Do you guys remember what it is? Under zoom? Yeah, it's zoom 9 for stat. So hit zoom 9, and there we go. There's a nice little sinusoidal function. And this makes sense because, like, in the winter, right, January 1st is the winter, you don't have very much sunlight, and then in the summer you get lots of sunlight, and then as you go back into the fall, you get very little sunlight again. Okay? So there is our scatter plot. So that would kind of confirm that this is in fact a sinusoidal regression that we should be doing. If we wanted to actually do the sinusoidal regression, what would we have to do next? Stat, again, yeah. And then go over to the right to calculate. And here's where all of our different options of regressions are available to us, okay? And just to review, in this course, the ones that we have done so far are number 4, this is a linear regression. Number 5 is quadratic, and number 6 is cubic. Those are the 3 polynomial regressions that we did, okay? We also did number 9. Do you guys remember what number 9 was for? The lawn regression? I didn't emphasize the lawns because we didn't really do much with them except for regression functions. Yes? No, stretching. Those were logarithmic regressions. Do you remember ln is the natural logarithm? Yes, some of you remember. Okay, I know it's been a while. And then 0 is exponential, so we did that one as well. And if you keep going all the way to C, this is the sinusoidal regression. So you're going to hit enter, because that's the one that we want to do. Okay? You are going to go all the way down. Now, if you see this menu, depending on your calculator, you may see this menu, you may see something, you may just see sine regression. If you see this menu, go down to where it says store regression equation. If you just see sine regression, rejoin us right now. And what we're going to ask the calculator to do is to store the regression function into y1 so that we don't have to copy it ourselves manually. And to do that, we need to hit the y1 button. And, sorry, Sarah, did you tell me there was an easier way to do this?
Yeah, alpha and then calc.
Right. You can hit the alpha button. And calc?
Yeah.
And there it is. It's number 1. Look at that. Okay. So the way that I always do it is I hit the variables button. I hit variables, and then I go enter for function and enter again for y1. But there you go. There's another one. Alpha, the calc button or trace, and then it just pops up. There you go. So we got the y1 in there. If you don't remember how to do this, that's okay, because you're still going to get the regression equation, and then you could just copy all the values down and enter them in yourself. And then we're going to go down. If you didn't see this screen, you just see sine regression y1, hit enter. If not, go down to calculate and hit enter again. And there we have it. Okay, so this is our sine function. Now, if you are asked on an assessment to give me the equation of the sine function, I do not want a equals 4.44, b equals 0.01 or 0.02 or whatever it is to the nearest hundredth, c equals negative 1.31, d equals 12.16. That is not a function. What I want is this. Y equals A. The A value is 4.44. 4.44 sine bx, so b is 0.02 to the nearest hundredth, x plus c, so c is negative 1.31, so you can just go minus 1.31 plus d, which is 12.16. Okay. Now, one thing that is incredibly important is that although you can answer with rounded values here for part A, you should not use rounded values to determine the rest of the answers. Okay, so if you were entering this in manually, you don't want to enter the function into y1 that we entered into part A. And I'll show you why. Let's think about this. What should the period of this function be? Think about it. We're thinking about hours of sunlight in days throughout the year. What do you think the period should be? Looking at days throughout the year. 365. Okay, well, the b value has been rounded to 0.02. So the b value is 0.02, and we wanted to get the period based on that. Put that into your calculator. 2 pi over 0.02. Tell me what you get. How much? 314? That is way off. 314 days is way off of 365. big time, not just a couple days, like a month and a half off. So you do not want to use the rounded value to answer any questions. Okay? All right, now let's answer some questions. What does the median value in the regression function represent in the context of the question? The median, what is the median value? 12.16. It's the middle value. What do you think it represents in the context? Middle value of the y values. What are the y values? What do they represent? What does the y column represent? Yeah. Hours of sunlight in the day. So the middle value of the hours of sunlight in the day is 12.6. Relate that to the context. What is that 12.16 rather? What does that mean in the context? What could you say about red deer and sunlight? And the 12.16. What word would you use? Average. Yes. Okay. The average hours sunlight during the year is 12.16 hours. Okay? Now, domain and range, well, the average is 12.16. How far below does it go and how far above? Now, for this part, actually, you probably do, because these values were rounded, let's look at this function, right? Because it should now be in y equals. There it is. And because of the fact that I went zoom 9 for zoom stat, my window should be very nice and set. So I should be able to find my minimum point and my maximum point, and that will help me get my range. Okay? I don't really want to do it based on the rounded values because they were rounded. So I'm going to go second, trace 3 for minimum, and it looks like I've got a minimum over here that I can use. If not, I'd have to extend my window settings a little bit, but I think this one will work because it curves up a little bit. There we go. Okay, so the minimum is at 7.72. That's the y value. Okay, so that's for my range, right? So if my range, the minimum number of hours is 7.72. The maximum number of hours is up here, 4. And that's at 16.59. It actually would have been fine to use the rounded values for this one, but we're not going to get into that now. So this is y, 16.59. It's good to look at the graph too. Okay, that's my range. Domain. What do you think the domain here should be? Domain represents days in the year. Yeah.
X cannot be bigger than 365.
Okay, yeah, so the biggest is 365. What's the smallest? 0. Yeah, and that's, again, we talked about this the other day, and I know it can sound confusing, right? but day 1 ends at midnight on January 1st. So if you're only at like 9 in the morning on January 1st, you're only at part of a day. You haven't completed the whole day yet. So you'd be at like a decimal point of a day. So it actually starts at 0. Okay, because time is continuous, right? It's not like we have day 1, day 2, day 3. We can have day 1.5. Day 1.5 is actually January 2nd at noon, because you're 1.5 days into the year. Yeah.
I was just wondering, like, if we write it as an X such that there will be greater than X, but then 5 days.
Oh, yeah, you want to write it using set builder notation?
Yeah.
Absolutely. So if you want to do this, right, you can write domain and range. This is the minimum expectation for this course. But you could also do this. You could go domain is the set of X such that 0 less than or equal to X less than or equal to 365, comma, X is an element of the real numbers. You could also do this. Domain, you could use interval notation if you want. Okay, you're never going to be given interval notation in a question, but you could respond with that. Yep.
Can you just scroll up to like the very top where you wrote that number at the very beginning?
Yeah. Which one?
Like at the very top about the, yeah, that.
Oh, this. Yeah. Yep.
So when there's a line on the graph that has some sort of calculator, I can put that on my calculator.
Okay. I'll come around in a sec. Now, that's it, you guys. That's the end of this unit. I want you to go on to the next page and try the example on the next page. But that's it. We're done. Now, hold on.